All right, this quiz is on fluid statics. So I got a few definitions, but remember, please read the textbook. There's just so much more going on than I can do in a few short videos. But let's go through some definitions. A fluid means either a liquid or a gas. I know in English, oftentimes when we use the word fluid, we think liquid as if those are synonyms. But a fluid in physics is anything that can flow. So that means liquids or gases, but not solids. All right, another important definition for this chapter is density. Density is mass divided by volume. The symbol for density is the Greek letter rho. I know it looks like a P, but it's not. It's a rho, R-H-O. And it's equal to mass divided by volume, which is measured in kilograms per meter cubed. Now, kilograms per meter cubed is a somewhat unfortunate unit because a meter cubed is a huge volume. It's such a huge volume. It's 1,000 liters and 1,000,000 centimeters squared, or centimeters cubed. It's just a really large volume, so much so that a cubic meter of air is 1.2 kilograms, and a cubic meter of water is 1,000 kilograms. So anyway, we're just going to have to deal with using some rather large numbers for density because a meter cubed is such a large volume. And also that means that a lot of times when we are doing volumes in problems, we're going to have really, really small numbers because, a normal sized object like my fist or something could be something like 10 to the minus 5 meters cubed because a meter cubed is such a large volume. Okay, and then we got pressure. Pressure is force divided by area. And so the symbol for pressure is a capital P. And the units for pressure are newtons per meter squared, which are the same thing as pascals. Now, there are lots of other units that people use for pressure. The one that you might be most familiar with is a PSI. PSI stands for a pound per square inch. And that's certainly a more familiar unit if you grew up in America. And there are other units that people use for pressure, like millimeters of mercury or bars, or there are lots of units for pressure. But when we're plugging in formulas in this class, we're always going to be using pascals. So always convert to pascals before we plug into any of our equations. Finally, I want to talk a little bit about atmospheric pressure. I've got a video on atmospheric pressure with some cool demos, but it's important to know that the air all around us has pressure. It's pushing on us in all directions. And in fact, it's a lot of pressure. It's 101,000, approximately 101,300 pascals of pressure, which is about 14.7 psi, or pounds per square inch. And that's just a lot of pressure pushing in on all objects. Now, what normally happens if you have an open container is that you've got this huge pressure on the outside pushing out on the container, and you also have the same huge pressure on the inside. I'm sorry, on the air on the outside is pushing in on the container, and the air on the inside is pushing out on the container, and those two forces just cancel each other, and so the net force on the container is 0, which is why it doesn't crush or blow up. But if we were to cap the container and then take away all of the air outside the container, what would happen almost certainly is that container would explode because there would be so much pressure pushing out on it and no pressure pushing in on it that container would just explode because 14 pounds per square inch is a lot of pressure. So if we were to fill a bottle up with air and then take it out into space where there's no air pressure, the air inside the bottle would push out on it and it would explode. Similarly, if we were to do the opposite, where we still had the pressure on the outside, so we have lots of air pressure on the outside pushing in, and then we took out the air from inside the container, what would happen is that the bottle would crush. And there are a couple of really cool videos showing that. But the thing to know is that there is a lot of pressure in the air around us. And we call that atmospheric pressure. And of course, it goes up and down every day. You have high pressure days and low pressure days. And weather people are very concerned about the current atmospheric pressure. And okay, so that's atmospheric pressure. And the last thing I want to talk about as a definition is the idea of gauge pressure versus absolute pressure. Now, let's go back to opening this little container so that we've got air on the inside and air on the outside. And so we've got air pushing on the outside, and we've got air pushing on the inside, and the pressure out here is 1 atmosphere, about 101,300 pascals, and the pressure on the inside is also 1 atmosphere, about 101,300 pascals. But you see that the net effect here is nothing, right? The air pushing on the outside of the bottle and the air pushing on the inside of the bottle exactly cancel each other, so it's almost like there's no pressure at all. So in fact, if we were to close off this bottle and put a pressure gauge on here, the pressure gauge would probably read 0. And the reason it would read 0 is because what the pressure gauge is reading is what's called gauge pressure, which is how much higher is the pressure inside compared to the pressure outside. So, for example, if we pump up a basketball and we pump it up to 7 psi, what that means is that the pressure inside is 7 psi higher than the pressure outside. So we've still got pressure outside, but the pressure inside is higher than the pressure inside. And so, okay, so ultimately, gauge pressure means the difference in the pressure between the pressure inside and the pressure outside. So usually what we mean by this is the pressure we're measuring minus the pressure of normal atmospheric pressure. So if I said that the gauge pressure was 50,000 pascals, that would mean that the pressure was 50,000 pascals above normal atmospheric pressure. So that would mean that the absolute pressure would be equal to 151,300 pascals, or 50,000 above the normal atmospheric pressure. So when we say gauge pressure, what we're talking about is the difference in pressure between the thing we're measuring and normal atmospheric pressure. So for example, in your tire, in your car, you're supposed to pump those up to like 35 psi. And what that means is it's 35 psi above atmospheric pressure. That's the gauge pressure. It means the pressure inside the tires is higher than the pressure outside the tires by that extra 40 psi. And again, I keep using PSI because that's what people normally measure pressure in America, in the United States. If you are measuring pressures, you typically measure in pounds per square inch, but that's not the physics unit. The physics unit is pascals, and so that's newtons per meter squared. And you can imagine actually a pascal is a very low pressure. 1 Newton of force is like an apple. 1 meter squared is a pretty large area, and if you spread out the force of one apple and spread it out over an entire meter squared of area, you can imagine that's a very small pressure. If you were to add that pressure to your skin, you probably wouldn't notice an increase in pressure of 1 psi. I'm sorry, of 1 pascal, because 1 pascal is not a very much pressure. Okay, so those are definitions. And then I just want to go over a short outline of what we're going to be doing this week. We're going to be talking about how the pressure of a fluid changes with depth, and that's due to gravity. We're going to talk about the fact that if you have a submerged object, either partially submerged or fully submerged, if you have a submerged object in a fluid, that fluid exerts an upward force on the object. We call that buoyancy. Okay, so fluids push up on submerged objects. And then lastly, we're going to look at surface tension, and this only deals with liquids. But surface tension is the idea that if you have a body of water, for example, this is made up of a bunch of little molecules, and all of these little molecules are attracted to each other. Now, if you're inside this little blob of liquid, you have some molecules above you, some molecules below you, some molecules to the left, some molecules to the right. And so you're attracted to this one, and you're attracted to that one, and you're attracted to this other one, and all those forces cancel. But if you happen to be one of the molecules on the surface, okay, you're pulled in by the other molecules, and you're pulled sideways by the molecules next to you, but you're not being pulled out because there are no water molecules or other kinds of liquid molecules on the outside of the little blob. So this results in a net inward force on the surface of the water or the liquid, and that net inward force on the surface is called surface tension. Basically, it's pulling all the different parts of this are pulling inward on each other. It's not unlike a balloon that's been blown up. All the rubber in the balloon is being pulled by all the pieces of rubber around it, and that creates a surface tension. And that surface tension has two effects that we're going to study. One, where if you have a bubble, for example, of soap water, that surface tension pulls in on all the edges. And what that does is it makes the pressure inside higher than the pressure outside. So there's some extra pressure inside because that air inside is being squeezed by the water bubble. And so we get a higher pressure on the inside. And we can calculate how much higher. The other interesting thing that we're going to look at is that if you have a bucket full of water or alcohol or any other fluid, and you stick a very skinny tube into it, what's going to happen is the water level in the tube is either going to go up or possibly go down based on the surface tension of the fluid. And so what I'm saying here is, if this fluid is filling this jar, this liquid is filling the jar, it could raise up in the tube, and that's called capillary action. It's actually also possible if we had a different liquid in the jar. Maybe this time I'll use a red liquid instead of a blue liquid. So if we have a different liquid in this jar, it's also actually possible that the level would be depressed. Instead of having the fluid go up the tube, we could have the fluid, below the, going down the tube, being depressed instead of being raised up. And again, that has to do with the forces between the molecules in the liquid and the forces between the molecules connected to the tube. And I've uploaded a couple of videos about that other people have written, and I thought they were better than any video I could make. So hopefully you'll find those helpful. All right, well, I'll come back in a little bit with some example problems. I'm going to focus on parts A and B because part C, I've uploaded videos from other people, and I actually thought the videos that they made are better than anything I could make. So hopefully you'll find those